Hello everyone. This chapter I'll focus on technical principles of Flume. Well, simply speaking, Flume is an open-source log system which is used for collecting, processing, and transferring data. So after this course, we'll be able to know what is Flume and its functions and positions in Fusion Insight. Also, I'll talk about system architecture, key features, and some application examples of Flume. First, let's take a look at Flume overview and architecture. Well, Flume is a distributed, highly reliable, and highly available massive log aggregation system. Flume supports customized data transmitters for collecting data. Flume also roughly processes data and writes data to customizable data receivers. Flume is applicable to the scenarios of efficiently collecting, aggregating, and moving large amounts of log data from many different sources to a centralized data store. While the use of Flume is not only restricted to log data aggregation, since data sources are customizable, Flume can be used to transport massive quantities of event data, including but not limited to network traffic data, social media generated data, email messages, and pretty much any data source possible. Flume provides the following functions: collect logs from a specified directory and save the logs to HDFS, HBase, or Kafka. Also, Flume can collect and save logs to a specified path in real time. Flume supports the cascading mode, which means multiple Flume nodes interwork with each other for aggregating data. Besides, users can customize the data collection. In Fusion Insight, the position of Flume is here, which is a distributed framework for collecting and aggregating data. Then let's take a look at the architecture of Flume. A Flume event is defined as a unit of data flow having a byte payload and an optional set of string attributes. A Flume agent is a process that hosts the components through which events flow from an external source to the next destination. A Flume source consumes events delivered to it by an external source like a web server. The external source sends events to Flume in a format that is recognized by the target Flume source. For example, an Afro Flume source can be used to receive Afro events from Afro clients or other Flume agents in the flow. A similar flow can be defined using a Thrift Flume source to receive events from a Thrift Think or a Flume Thrift RPC client, or Thrift clients written in any language generated from the Flume Thrift protocol. When a Flume source receives an event, it stores it into one or more channels. The channel is a passive store that keeps the event until it's consumed by a Flume sink. The sink removes the event from the channel and puts it into an external repository like HDFS, or forwards it to the Flume source of the next Flume agent in the flow. The source and sink within the given agent run asynchronously with the events staged in the channel. Also, Flume allows a user to build multi-agent flows where events travel through multiple agents before reaching the final destination. Sources are just the source of data. The Flume can model and abstract the raw data as a data object that can be processed by the Flume, which is called event. Channel processor is to save the data transmitted from the source to the channel. Interceptor is to filter and modify the collected data based on the user configuration. Channel selector is to save the data to different channels based on the user configuration. The main function of channel is just to temporarily save the data. Sync runner is to drive sync processor, and the sync processor drives the sync to obtain data from the channel using different policies based on the user configuration. Currently, the policies include load balancing, failover, and straight-through. And the main function of sync is just to obtain data from the channel and save the data to different paths. An event is a minimum unit of a data string. It's transmitted from the external data source to the destination. While to be more specific, a source receives data and generates data by a special mechanism and places the data in batches in one or more channels. There are two types of source, data-driven and polling. For data-driven, the external source actively sends data to Flume to drive Flume to accept the data. And polling means that Flume periodically obtains data in an active manner. There are some typical source types. syslog is a source that are integrated with the system. It reads syslog data and generates Flume events. There are two types of syslog source. The UDP source treats an entire message as a single event, and the TCP sources create a new event for each string of characters separated by a new line. Exec is a source that automatically generates events. It runs a certain command or script and regards the execution results as a data source. Exec source runs a given Unix command on startup and expects that process to continuously produce data. If the process exits for any reason, the source also exits and will produce no further data. And Afro is an IPC source that is used in the communication between agents. When paired with the built-in AfroSync on previous Flume agent, it can create tiered collection topologies. Remember that a source must be associated with at least a channel. Channel locates between source and sync. A channel caches received data and sends the data successfully processed by sync to the next channel or final destination. The data is then removed from the channel. Different channels provide different persistency levels. Memory channel does not support persistency. The persistency of file channel is based on WAL, which is write-ahead log, and the persistency of JDBC channel is implemented by embedded database. Channel supports transactions. When Flume transmits data to the next process over the channels, if something goes wrong, data will be rolled back and saved in the channels, waiting for the next processing. Channel also provides weak sequence guarantee and can work with any number of sources and syncs. Three kinds of channels are mentioned earlier. For a memory channel, the events are stored in an in-memory queue with configurable max size. It's ideal for flows that need higher throughput and are prepared to lose the staged data in the event of an agent failure. File channel supports data persistency to disk. Here note that, by default, the file channel uses path for checkpoint and data directories that are within the user home as specified above. As a result, if you have more than one file channel instances active within the agent, only one will be able to lock the directories and cause the other channel initialization to fail. It is therefore necessary that you provide explicit paths to all the configured channels, preferably on different disks. Furthermore, as file channel will sync to disk after every commit, coupling it with the sink or source that batches events together may be necessary to provide good performance where multiple disks are not available for checkpoint and data directories. As for JDBC channel, the events are stored in a persistent storage that is backed by a database. The JDBC channel currently supports embedded Derby. This is a durable channel that's ideal for flows where recoverability is important. Sync is responsible for sending data to the next hop or final destination and removing the data from the channel after successfully sending the data. A sync must function with a specific channel. There are some typical sync types as follows. Syncs that send storage data to the final destination, such as HDFS and HBase. HDFS sync writes events into the Hadoop distributed file system. It currently supports creating text and sequence files. It supports compression in both file types. The files can be rolled periodically based on the elapsed time or size of data or number of events. It also buckets or partitions data by attributes like timestamp or machine where the event originated. The HDFS directory path may contain formatting escape sequences that will be replaced by the HDFS sync to generate a directory or file name to store the events. Using this sync requires Hadoop to be installed so that Flume can use the Hadoop jars to communicate with the HDFS cluster. HBase sync is to write data to HBase. This sync provides the same consistency guarantees as HBase, which is currently row-wise atomicity. In the event of HBase failing to write certain events, the sync will replay all events in that transaction. In addition, the HBase sync supports writing data to secure HBase. To write to secure HBase, the user the agent is running as must have write permissions to the table the sync is configured to write to. And AFRO is an IPC sync that is used for communication between agents. This sync forms one half of Flume's tiered collection support. Flume events sent to this sync are turned into AFRO events and are sent to the configured hostname or port pair. The events are taken from the configured channel in batches of the configured batch size. Then let me introduce some key features of Flume. First, Flume can collect logs beyond a cluster and save the logs in HDFS, HBase, and Kafka for data cleaning and analysis by upper layer applications. Flume can be configured to multiple sources, channels, and sinks. The above example shows 3 different sources to 3 different channels, and finally sync to different places such as HDFS, HBase, and Kafka. Flume also supports cascading of multiple Flume agents, as shown in the figure. In order to flow the data across multiple agents, the sync of previous agent and source of the current agent need to be AFRO type, with the sync pointing to the host name or IP address and port of the source. Data transmitted between cascaded Flume nodes can be compressed and encrypted. In this case, the data transmission efficiency and security can be improved. Note that the encryption depends on the storage medium and the sync type when synced to storage medium, and the progress from source to channel, then to sync, doesn't need to be encrypted. It belongs to data exchange within a process. Flume supports monitoring indicator presentation over the Fusion Insight Manager, including the received data size of the source, data buffer size of the channel, and written data size of the sink. Flume also supports alarms for channel, buffering failure, data transmission failure, and data receiving failure. The events are staged in a channel on each agent. The events are then delivered to the next agent or terminal repository like HDFS in the flow. The events are removed from a channel only after they are stored in the channel of next agent or in the terminal repository. This is how the single agent message delivery semantics in Flume provide end-to-end reliability of the flow. Flume uses a transactional approach to guarantee the reliable delivery of the events. The sources and sinks encapsulate in a transaction of the events so we can make sure that the set of events are reliably passed from point to point in the flow. In the case of a multi-agent flow, the sink from the previous agent and the source from the next agent both have their transactions running to ensure that the data is safely stored in the channel of the next agent. The figure shows the data exchange between agents. When data flows from one agent to another agent, the two transactions take effect. Let's regard this part as agent 1 and this part as agent 2. So, sink of agent 1 needs to obtain a message from a channel and sends the message to agent 2. If agent 2 receives and successfully processes the message, agent 1 will submit a transaction. This indicates a successful and reliable data transmission. When agent 2 receives the message sent by agent 1 and starts a new transaction, after the data is processed successfully, which means written to a channel successfully, agent 2 submits the transaction and sends a success response to agent 1. Before a commit operation, if the data transmission fails, the last transcription starts and retransmits the data that fails to be transmitted last time. The commit operation has written the transcription into a disk. Therefore, the last transcription can continue after the process fails and restores. During data transmission, if the next hop Flume node is faulty or receives data abnormally, the data will be automatically switched over to another path. Flume also has the capability to roughly filter, clean, or even drop unnecessary data during data transmission. This is done by the help of interceptors. An interceptor can modify or even drop events based on any criteria chosen by the developer of the interceptor. Flume supports chaining of interceptors. This is made possible by specifying the list of interceptor builder class names in the configuration. Interceptors are specified as a whitespace separated list in the source configuration. The order in which the interceptors are specified is the order in which they are invoked. The list of events returned by one interceptor is passed to the next interceptor in the chain. Interceptors can modify or drop events. If an interceptor needs to drop events, it just does not return that event in the list that it returns. If it's to drop all events, then it simply returns an empty list. Channel selector here is to transmit data to different channels based on events, which providing the routing function. Here also shows two examples of Flume. First one is about how to collect logs from an online banking system to HDFS by loader. We need to create a log directory in the cluster first. and take this directory as the monitoring directory. Then we log into Diffusion inside Hadoop to download and install the Flume client. This page shows how to configure the source of Flume. Here we choose spooling directory source. Then to configure Flume channel, here we choose memory type, and other parameters are basically by default. Then to configure Flume sync, here we choose HDFS type, which means that the data will be transmitted to HDFS. After completing the configuration file, name the file as properties.properties and upload this file on Diffusion Insight Management page. Then, move data files to the monitor directory and use this command to check if data is synced to HDFS. If succeeded, the file will be renamed with a completed suffix. The other example is about how to collect real-time clickstring logs to Kafka by Loader. The process is almost the same. The source configuration is very similar to the first example. Also, the channel configuration is same as before. The difference is about the sync. Here we choose Kafka sync type, and we need to specify the topic. Then, upload the configuration file and use Kafka commands to check data. So this chapter mainly talks about Flume, including its functions and application scenarios and also configuration methods. Okay, that's all for Flume. Thank you.